Okay. So yeah, from all that we're doing here, apparently these Riemann sums, these sums of the rectangles, that's kind of an important deal. And like I said, that is our next place we need to go. And so, just like the slopes, the limits of those secant lines, what it turned into derivatives, these rectangles, yeah, they turn into what we call integrals. It's called the definite integral. So this is our definition of the definite integral. If f is a continuous function from a to b, write it all down here. Then the definite integral of f from a to b is defined this way. If f is a continuous function for a is less than or equal to x, less than or equal to b, so we're talking about the same setup here. It's a continuous function now. It doesn't have to be continuous. Then the definite integral of f from a to b is this. The symbol, if you haven't seen it before, is a little funny looking S. You put a and b, well, a is a subscript, b is a superscript, if you will, something like that. F of x dx. We've seen dx before. We're bringing it back to life here. That's what an integral looks like, if you haven't seen it before. Here's what it equals, though. Turns out this integral is equal to that precise net area we defined a while ago. Remember what it was? It was the limit as n goes to infinity of the sum I equals 1 to n of f of x of I star times delta x, because you can use right endpoints, you can use left endpoints, whatever you want to. We define it. This is the integral, the definite integral. So what does this mean? Well, it's this. And what is this? This is the infinitely many rectangle area under the curve formula there. That's what an integral is. That's what it represents graphically. Okay? Now, just some notational things. This symbol is the integral sign. What you're taking the integral of f of x here, the function, is it's called the integrand. A and b are said to be the limits of the integration. So you put your limits, you got an upper limit, you got a lower limit, those are called your limits. And dx is used, one thing it's used for is to tell you what you're integrating with respect to. Because if I'm integrating with respect to y, that's probably a different thing than integrating with respect to x, right? It is. Okay? So the dx, or whatever the d is here, that tells you what you're integrating with respect to. And essentially, if you think of the graphical aspect, it tells you which way your rectangles need to go. Do they go vertical? Do they go sideways? dx, we're talking the up and down rectangles. But anyway, we'll get to more of that later. Yeah, that's where you're going from to 2. Yes. A to B is where you're going from to 2. All right. So if I draw the picture here say I've got this curve, A to B. How would I label that? Where would that be on this graph? Where would this integral from A to B f of x dx be on this graph? Huh? A to B x to x, yes. It's the area under the curve, yes. Here's the integral right here. That area in there, that's your integral from A to B of f of x dx. Okay? So if it ever asks you to label the integral, draw your curve, label it. Now, if my function happens to right there, what about there? Where's the integral there? Well, the integral there is the area between the curve and the x-axis, so it's here, here, and here. It's that area there. However, what do we know about that? Integral from A to B f of x dx. Yeah, this is going to be a positive value, this is going to be a negative value, and that's going to be a positive value. So I've got some positive, some negative. So the integral, what is it? It's that net area, right? Whatever this is, minus whatever that is, plus whatever that is. Okay? So the integral factors that in, right? How do I know that? Well, that's what this does, right? If f of x goes below the x-axis, these rectangles are going to be negative, right? Negative areas for below the x-axis, because that's going to be negative. The function values are going to be negative down here. So hence, these are going to be negatives. These are going to be positives. Okay? All right. Okay, so now, then, we do need to talk about the other part of the handout. So back to the handout here. Let's estimate, let's go up here, the integral from 0 to 6 f of x dx with 4 subintervals and right-hand endpoints. Okay. Estimate that integral. How would I do that? Same way we've been doing it, right? This is the exact same thing. I'm doing the rectangles, 0 to 6, 4 subintervals. So I want to go from 0 to 6, put 4 subintervals in there, do the rectangles. The exact same thing. To estimate this is to estimate the area between the curve and the x-axis, just like we were doing. We haven't done anything different yet since last time. Okay? We're still doing the same thing. What is my delta x? What's my width? 6 minus 0 divided by 4, right? Endpoints, difference, divided by 4, 6/4, which is 1.5. So each of these is 1.5 wide. So the first one's here, using right-hand endpoints. And sorry about the bouncing there. So that first one looks to be about that. So that integral, the integral from 0 to 6 f of x dx, is approximately equal to what is that, 1.5 by, what is the height? Depends on which moment I want to take it. 11. Okay, let's go with 11. All right. What about the second one? Well, the second one, I'd go from 1.5 to 3, wouldn't I? Right-hand endpoint, so I'm going to go about there. So let's call that 4.5. Take an average. Is everybody with me on that? Second one, what about the third one? Well, the third one would be where at? 4.5? Because I'm going 1.5 each time. So the third one would be at 1.5, but where is it? It's down here, isn't it? Oop, too far. So the third one would be right there. Try that again. Not quite that low. So what do you got for it? 1.5 by what? What's the height? -3. Okay? Everybody see where we get that? -3, since it's down here. It's negative. So that's going to counteract the ones that are up here, positives. And then at 6, is 6 right down there at the, is that 6 at the bottom? I think so. So the fourth one would be right there. Okay, and so that would be -9. So it'd be 1.5 by -9. So it looks like we're going to come out positive in the end. .25. So the integral is approximately 5.25 because that is the net area we get with these rectangles. Questions or concerns? Yeah, that one would be hard to tell, wouldn't it? Because you got some that's, this one kind of counteracts, so that one's about good, but this one's definitely underestimate. You got a little over here, don't you? Yeah, you have some positive with negative. Yeah, that's what I'm saying. It'd be hard to tell kind of with that one, if whether's, and they usually won't ask you unless it's obvious, so yeah, all right. They usually won't ask you if it's an underestimate unless it's obvious. Okay, so what would this one be? For B, the integral 1 to 5, f of x dx. Again, 4 subintervals, left-hand endpoints. What do you got there? Well, this one, I changed it up. I'm going 1 to 5. So I'm estimating from 1 to 5 here. I want 4 subintervals. Now this, with 4 subintervals, where am I looking at? Delta x would be 5 minus 1 divided by 4. So that would be 3/4, 0.75. Oh, yeah, it's not that bad, is it? 4/4. It's 1. Yeah, there we go. Sorry about that. Okay, so I am just going at 1, so that's good. So the first one, so how tall is the first one? It's 1 wide. How tall is it? Well, I'm using left endpoints, so I come here to the left one, and that was there at that peak, isn't it? So that would be the integral 1 to 5 f of x dx is approximately equal to, the first one's 1 by, what, 11.2 or 11.1, whatever you want to say it is. It's a little above 11, I think. My eyes aren't deceiving me. Maybe, yeah, 11.2, something like that. What about the second one? Well, the second one, I just come out, go another 1, so that gives me to 3. Using left-hand endpoints, though, so I come to the one at 2, don't I? So I'd be that tall there. So that's, is that right at 9? It's kind of hard to see on the board there. Huh? 9.5? Okay. Like I said, these are just kind of estimates anyway. So The third one would be right at 4, right? But I'm using left-hand endpoints. If I was using right-hand endpoints, it would be a 0. So it's not. It's right there. So let's call it there. And that's about 5.5. I'm going to call it. And then the last one, 4 to 5, use left. What happens on the fourth one? Well, if I use the left-hand endpoint, it's right at 0, isn't it? So that last one, there's really no rectangle there, so it's 1 by 0. Okay. All right. What do you got there? So basically, it's 11.295 and 5.5. So the negative, using the left-hand endpoints, the negative part doesn't even show up. That's okay. $26.2. Yes, thank you. So this integral is about 26.2. All right. Now, I believe the last thing I wanted to look at with you is on the back side there. Talk about it. Go ahead and do it. Because these are just estimates. But if you look on the back side, let me see if I can find my problems there. Oh, there they are. Will you mind scrolling me up? There you go. Yeah, that's good. Thank you. All right. You know, when you've got nice graphs, straight lines and all that, here's the thing we could point out on this. Actually, we can do this integral computation kind of a... yeah. It is continuous. There's no breaks. It's not differentiable. Maybe that's what you're thinking. Okay. Here's the thing. We can get the exact value for this one. We don't have to use the rectangles, in other words, what we're saying. I mean, we could use still the rectangles to get an approximation, but here we can get an exact value. Because I'm looking at the integral 0 to 4. What do you see if I go from 0 to 4? What do you see in this area here? Triangle and rectangle? Yeah. I guess depending on how you do it, you can divide it up different ways. Let's see. Yeah, knowing that this is the area under the curve, yeah, if I can just calculate that area using triangles and rectangles, then that gives me an integral, doesn't it? Because the integral is the area under the curve. How do I want to do it? Well, maybe do it this way. Probably the easiest way. Two triangles and a rectangle. How about that? So this exact value is whatever the area of that triangle is, whatever the area of that triangle is, plus the area of that rectangle. Okay? Triangle 1 plus triangle 2, that's what we're saying. Just take the area of the triangle plus the area of the other triangle plus the area of the rectangle. That way we compute the exact area under the curve. Now, of course, most curves aren't nice straight lines like this, so these are exceptions to the rule. But it does emphasize, the reason I like these is it emphasizes that the integral is the area under the curve. All right, so what's triangle 1? It's a half. Triangle formula is 1/2 base times height, right? So it'd be 1/2, the base is 2, the height is 1, 2, 3. Triangle 2, well, it's a triangle, and it's a half by 2 by 4. And then the rectangle is a 2 by 1. Half of 6 is 3, half of 8 is 4, and 2, so you got area is 9. So that's the integral value, definite integral. Okay? All right. What happens, the other two, let's talk about what happens for this. Everybody okay on that? All right. So y'all move down to B. I'm not even going to have to move here. I'll just erase. Everybody's got it. Okay. So B. What about this integral? 4 to 6 f of x dx. Well, that's this area here, isn't it? Triangle area. So it's again a half base times height. The base is 2, but what's the height? Minus 4. Yeah. Isn't that integral going to be negative? Because it's y. Why is it negative? Below the x-axis. So yeah, your triangle is below the x-axis, so that makes it a negative 4. Okay? All right. Last but not least then, for C, let's do the integral from 0 to 8 f of x dx. All right, so 0 to 8. Aha! So there, we've got this area, then we've got the area below, and I've got another area above. Well, of course, if we hadn't done it already, we could do the rectangle and triangle thing there, but I think we've already got it there, right? That was, what was it? That one was 9 for, for 0 to 4. So I'm not going to go through all that again. Now, I didn't quite do all of this one. I did 4 to 6, so let's do that one again. The triangle here in the middle, it would be 1/2 base times height. The height is negative, the base is 3, the height is negative 4, so that would be a negative 6 there. So that's for 4 to 7. And then the last one, well, it's a little small one, so it's a half by, what, 1 by 4? So yeah, we got 9 minus 6 plus 2. Is that 5 for C? Yeah, so you got the give and take. This one is going to be a negative 4 to 7. So, okay? Let me mention one more. That's kind of lied to you there. One more and I'll be done. Like I said, they're not all what this is not at all how we'll be doing these, but just like I said, getting you to the point thinking integral as area. This one has nothing to do with the handout, but we can kind of work our way around this one if we know what we're talking about. If I want to know the integral negative 4 to 4 of 16 minus x squared square rooted dx. Nope. What you have to realize is what this right here is. If I say y or f of x equals the square root of 16 minus x squared, I think we might have talked about it before. It's basically the same as y equals 16 square root of 16 minus x squared, which is the same as y squared equals square both sides, 16 minus x squared. So move the x squared over. It's the same as this. Maybe that's more familiar to you. What is that? Circle, yeah. This, though, is not the full circle, because if we wanted the first full circle, I'd have to go plus or minus. What is this? It's the top half of a circle. Semicircle. Yeah. Yeah, it's a semicircle. Okay, so with all that in mind, I want the integral from -4 to 4. Well, if you put that in your calculator, here's what you get. Semicircle from -4 to 4. The top half of the circle from -4 to 4. How can I calculate the integral of that? I'm trying to find this area. Well, isn't that half of a circle? Half pi r squared? Yeah. So we did triangles. This is a circle, half of a circle, so we can do it that way. Half pi r squared, which is half of, what's the radius? Isn't the radius 4? Yeah, so it'd be 8 pi. Or 8 times 3.14 if you like. Okay? So anyway.